Hello everyone, this is going to be a very different video to what I usually make. I always make videos about the Rubik's Cube, but today I want to talk about something else that I'm very passionate about, and that is math. So you've probably seen the title and you went to yourself, well, the square root of -1 is I, which is the definition of a non-real number. But today I'm going to prove you otherwise, if you just bear with me for the next couple of minutes. Before we start the proof, there are a couple of formulas that I'm going to refer to all throughout the video. The first one is this: e to the ix equals cosine of x plus I times sine of x. This is called Euler's formula. The second one, e to the I pi equals -1, also a very famous math equation, and I'm going to assume that both of those are true all throughout the video. Alright, let's start. At first, I want to take this formula, e to the I pi equals -1. Now, what I'm going to do is take the square root of both sides. What I get is e to the I pi over 2, because taking the square root is the same as dividing the power by 2, equals square root of -1, which, as we all know, is I. Now, look what we have here. E to the power of some number equals I, which means that this number, I pi over 2, is the natural log of I. Remember this, it's going to be important later. Next thing I want to do is take this formula and raise both sides to the power of I. On the left side, I'm going to write this first. It is just I to the power of I, which is easy. And on the right side, this is going to be e to the I pi over 2 to the power of I. And if you know index laws, that means that we can just multiply the powers and we get e to the negative pi over 2, because I times I is just -1. So this number is a real number and it is equal to about 0.2. So I to the power of I is a real number. This is something famous, it's been done before, and remember that because it will be important for later. Next thing I want to do is see what happens when I raise some number a to the power of I. This is the same as writing e to the power of natural log of a all to the I, because e to the ln a is just a. So if you know your index laws, again, we can just multiply the powers and you get e to the power of I times natural log of a. And now this looks very similar to this Euler's formula. If we just plug in ln a as x here, we get that this is equal, a to the I is equal to cosine of natural log a plus I times sine natural log of a. Right, now we got everything we need. So what I'm going to do right now is I want to calculate what I to the I is with this formula. So if I plug in I instead of a, we get that I to the I equals cosine of natural log of I plus I times sine of natural log of I. But I know what I to the I is, I put this here, and I know what the ln of I is, this is this. So if I plug in everything, I get that I to the I, or e to the negative pi over 2, equals cosine of natural log of I, which is I pi over 2, plus I times sine of, again, natural log of I is I pi over 2. But we know that this is a real number, so the imaginary part of this number is going to be 0. So we can delete this term, I times sine of natural log I, because we know that it's only real. So look what we have now. Cosine of I pi on 2 equals e to the negative pi over 2. We can just take the inverse cosine of both sides and we get I pi over 2 equals 2 inverse cosine of e to the negative pi over 2. As you might remember, this number is equal to around 0.2. So it is completely normal to take its inverse cosine and we get a real number. And now we can just multiply both sides by 2 over pi and we get I equals 2 times the inverse cosine of e to the negative pi on 2 all over pi. This is a completely real number. It is equal to around 0.7866, and that's it. Now this is wrong. If you square this number, you're not going to get -1. But this whole proof was just me having fun, and I hope you had fun as well. I think it's very interesting and pretty funny to find things like this in math. And that's the whole point of the video. That's it for today. That was my first math video on this channel. I don't think I'll be making more math videos. It was just this one thing that I found really interesting and funny, and I decided to share it with the internet. So until next time, subscribe,